So by using the chemical potential framework, we were able to derive classical equations that relate the composition of a liquid phase to a vapor phase. So we were able to derive Raoult's law, which once again assumes ideal solution behavior. And we're also able to derive Henry's law, which applies for species that have sparring solubility in the liquid phase. Of course, some of the assumptions we made in throughout this derivation are a little bit tricky. So to kind of augment the explanation, we could also think about these equations visually. And so in this illustration, or in this schematic, what I'm plotting is on the left-hand side, or the y-axis, it's the partial pressure of some species of 1. And on the x-axis, it's the mole fraction in the liquid phase. Now, let's think of, water, or let's just think of some species that obeys Raoult's law, right? And so this black line here that I'm pointing to, this is a visual representation of Raoult's law. And in Raoult's law, we saw that the partial pressure of some species is just linearly proportional to the mole fraction in the liquid phase. And so as we go from 0 to 1, it's just going to be a straight line relationship. And when the mole fraction is equal to 1, we see that the partial pressure there, because we just have the pure species, is just going to be equal to the saturation pressure of that species 1. Okay? All right, so that's what Raoult's law is representing. Let's now think of a species in which it only has limited solubility in the liquid phase. Okay? And so that's what this blue line represents here. When the mole fraction of that species is very low, initially we'll see some sort of linear behavior between a mole fraction of 0 and some mole fraction x. Okay? So we see some sort of linear behavior here, but as soon as we start increasing that mole fraction, we'll see deviation from linearity. Right? When the mole fraction is equal to 1, right, we're going to get the true vapor pressure of that species. Right? But if we go back to this linear sort of relationship, and we extrapolate the linear line to a mole fraction of 1, we see that the extrapolated value is different than the actual true value of the vapor pressure, or of the saturation pressure. Okay? And so what Henry's law is saying is that if you extrapolated the linear portion of the curve to a mole fraction of 1, this sort of hypothetical vapor pressure would be your Henry's law constant. So I'll just say this is going to be the Henry's law constant. Okay? All right, and so, once again, Henry's law constant is just the extrapolated hypothetical sort of saturation pressure. It's not equal to the true saturation pressure there.